Hi there. Today we're going to be discussing the gyrocompass. The gyrocompass is a device often used on ships and submarines to detect the true location of north. It comprises a rotating disc or more general shape, spinning with an angular velocity omega, which is very large. The compass is confined to a horizontal plane, and over time the axis will align itself with true north when the ship is not moving, and it will align itself at a predictable angle to true north if the ship is in motion. First, let's draw the Earth. And we'll introduce a vector going from the centre of the Earth to the North Pole, and we'll call this vector A, being a unit vector. Let theta be the colatitude. Now we'll set up a basis. We'll have unit vector EZ radially outwards. E north will have pointing in a horizontal plane towards the north, and there will be a vector E east into the screen. This means that the set E east, E north, EZ is an orthonormal right-handed basis. Suppose the ship has angular velocity omega v equal to theta dot E east plus phi dot times A. So in other words, it's rotating with angular velocity phi dot around in that direction, and theta dot would be, that's your easterly direction, that's theta, so theta dot corresponds to southerly motion. From this we can compute the velocity of the ship. V is omega v cross r times Ez, where r is the radius of the Earth. So that gives me theta dot E east plus phi dot times A cross r Ez. Now A is equal to sine theta times E north plus cos theta times Ez. And we can see that from a diagram like this. That angle is theta, so that's the component in the northerly direction, and that's the component in the z direction. So that's theta dot E east plus phi dot times sine theta E north plus cos theta Ez crossed with r times Ez. Of course that term goes, and that gives me r theta dot E east cross Ez plus phi dot sine theta E north cross Ez multiplied by r. And east cross z is minus r theta dot E north plus r phi dot sine theta. E north cross Ez is E east. And so that's V north, E north, V east, E east being the components of velocity. And therefore omega v I can also write as minus V north over r times E east plus V east over r sine theta times A, and that's coming straight from this expression. Assume that the gyrocompass lies at an angle alpha to true north, so write the axis of the gyrocompass as n. So the gyrocompass is spinning about this axis. So n is cos alpha times E north, because that's the E north direction, and that's the east direction, so you have plus sine alpha E east. So the angular velocity of the compass is going to be omega, capital Omega, which is scalar omega times n, where omega is a lot larger than little omega, where little omega is 2 pi radians per day, the angular velocity of the Earth. So in vector form, omega for the Earth is scalar omega times vector A, again A corresponding to the direction straight up through the North Pole. Let m be minus sine alpha En plus cos alpha E east. So this is orthogonal to n, and also it is orthogonal to Ez, and m squared is 1, so it's of unit length. So A, if you remember, was sine theta E north plus cos theta Ez is equal to sine theta cos alpha n minus sine theta sine alpha m plus cos theta Ez, where we have used that E north is cos alpha n minus sine alpha m, and E east is sine alpha n plus cos alpha n. Now alpha is free to vary, so there is an angular velocity alpha dot Ez accounting for this motion. To summarize, there are four motions corresponding to the angular velocities omega v, corresponding to the direction of motion of the ship. Omega, which was omega a, was the rotation of the Earth. Omega being scalar omega n, corresponding to the driven rotation of the gyrocompass, and alpha dot Ez corresponding to the rotation of the gyrocompass around its vertical axis. These two have rotations about the centre of the Earth. The last two are rotations about the centre of mass of the compass. Now let's work out the velocity of a general point in the compass. There are four contributions. V1 is omega n cross x, where x is the location of the point measured relative to its centre of mass. In other words, the integral of x times rho d3x is 0. V2 is V1 plus alpha dot Ez cross x. That corresponds to the rotation in the horizontal plane of the compass. V3 is V2 plus omega a crossed with x plus Rez. This corresponds to the rotation of the Earth about an axis through the centre of the Earth. And V4, which is actually x dot now, is V3 plus omega v cross x plus Rez. So putting that all together, we have that x dot is omega total cross x plus omega a plus omega v cross Rez, where omega total is alpha dot Ez plus omega n plus omega a plus omega v, and that's alpha dot Ez plus omega n plus omega primed a minus Vn over Rez, where omega primed is omega plus Ve over r sine theta. So that's equal to n times omega minus Vn over r sine alpha plus omega primed sine theta cos alpha minus m times omega prime sine theta sine alpha plus Vn over r times cos alpha plus Ez times alpha dot plus omega primed times cos theta. Now work out the kinetic energy of the gyrocompass. T is a half the integral of rho x dot squared d3x. It's a half the integral of rho times omega total cross x plus omega a plus omega v cross Rez squared d3x. That's a half the integral rho omega total cross x squared d3x. We get a cross term and this final term here. This term vanishes because the integral of rho x d3x is 0. That's equal to a half omega total transpose I, where I is the inertia tensor, omega total plus a half m omega a plus omega v cross Rez all squared. And this term is independent of alpha and alpha dot. This term we'll call T rot. So T rot is, well, we compute this by taking the expression we have here, multiplying coefficient of n squared by c, and then multiplying by a the sum of the squares of the other two components. So that gives us a half c into omega minus Vn over r sine alpha plus omega prime sine theta cos alpha all squared, plus a half a times alpha dot plus omega cos theta all squared, plus omega primed sine theta sine alpha plus Vn over r times cos alpha all squared. From the kinetic energy, we can construct a Lagrangian. L will just be T, there is no potential energy term. So that's T rot plus half m r squared omega a plus omega v cross Ez all squared. Let's consider the special case when the ship is not moving, so v equals 0. In which case omega primed is the same thing as omega, the rate of rotation of the Earth, and then we can have a new Lagrangian, just dropping terms from the original Lagrangian, which are constant. So we have L prime as a half a alpha dot squared, there's a half a omega squared sine squared theta sine squared alpha, I've used a trig identity there, plus a half c into omega plus little omega sine theta cos alpha all squared. And then we have the total derivative of a alpha omega cos theta, which corresponds to the cross term when I expand that term there. I've also dropped this term because it doesn't depend on alpha and alpha dot, so it doesn't make any difference to the equations of motion. We've also dropped a term which is a half omega squared cos squared theta, again because it doesn't depend on alpha or alpha dot. So now we can drop the term which was the total derivative. Therefore L prime is a half a alpha dot squared minus V of alpha, where V of alpha is an effective potential, to minus a half a omega squared sine squared theta sine squared alpha minus a half c omega plus little omega sine theta cos alpha all squared. We can expand the squared term, minus c omega times little omega sine theta cos alpha, that's the cross term we get from here, minus a half c minus a omega squared sine squared theta times cos squared alpha, minus a half a omega squared sine squared theta minus a half c omega squared. We converted the sine squared into a cos squared to get that term there. That term is just a constant, so if we want we can ignore it. If sine theta equals 0, in other words we're at a polar rotation, then V alpha is constant and therefore alpha dot is constant. So there is no minimum of the potential and the gyrocompass fails to work at the north and south poles. If sine theta is not 0, then have a look at equilibrium points. They correspond to V prime of alpha equal to 0. Well, that's equal to omega sine theta sine alpha times c omega plus c minus a omega sine theta cos alpha. We will spin the gyro up fast enough so that c omega is a lot greater than c minus a magnitude times omega. And therefore this factor is not 0. Therefore we get a maxima or minima only at alpha equals 0 or pi. So imagine omega being very large, greater than 0. Then you can see the potential is approximately, V alpha is approximately minus c omega omega sine theta cos alpha. If we just plot that, we'll end up with a cosine curve here, and you can see we have a minimum at the potential at alpha equals 0, and that's a stable equilibrium. So the gyrocompass will oscillate backwards and forwards about its equilibrium, and if we were to introduce some damping into the system, it would line itself at a value of alpha equal to 0. In other words, the gyrocompass will point in the northward direction. Now what if the ship is moving? So what if V is not 0? In which case the Lagrangian is going to be a half a times alpha dot plus order omega prime terms, all squared, plus a half c omega minus Vn over r sine alpha plus omega prime sine theta cos alpha all squared, plus order omega prime terms again. Now we're going to be spinning this up very fast, so actually this is the most important term, this capital omega. Lagrange's equation of d by dt dl by d alpha dot is dl by d alpha. So we're going to get a alpha double dot plus order omega prime terms is equal to c omega minus Vn over r sine alpha plus omega prime sine theta cos alpha times minus Vn over r cos alpha minus omega prime sine theta sine alpha. And we're interested in solutions where alpha double dot is 0. We know that this term here is approximately omega. So this is very large, so therefore this thing must be very small. So we need to take tan alpha to be equal to minus Vn over r omega primed sine theta plus an error term omega primed over capital omega. And we can make this term as small as we like if we spin the gyrocompass up to large enough speeds. So in other words, alpha is inverse tan Vn over r omega sine theta plus Ve. That's substituting the value for omega primed, if you remember. Omega primed was equal to omega plus Ve over r sine theta. So roughly how big is alpha? Well, if sine theta is about half, and the northward component of the velocity is, say, 20 miles per hour, our omega, the tangential velocity at the equator, that's about 1,000 miles per hour. This gives a value of alpha of about 2.3 degrees. So it's a relatively small correction, but obviously over time, or if you're in a submarine, it might be important for long distance navigation. Now, in retrospect, the final answer can also be seen by taking the Earth. We have our ship here, and it's moving in a direction. It has a northward velocity given by this, but it has an eastward velocity in the inertial frame of this thing plus the rotation of the Earth, so it's in that direction. That gives us an angle alpha, and that corresponds to rotating not about this axis, but an axis which is shifted by an angle alpha. So in this case, our gyrocompass pointing in a direction here with this value alpha, and again you can see alpha is therefore the inverse tan of the northward component of velocity divided by the eastward plus our omega sine theta, that last term corresponding to the tangential velocity of the Earth at that latitude. Now, one thing we might want to do is introduce some damping into the gyrocompass. If alpha naught is inverse tan Vn over Ve plus r omega sine theta, then our differential equation is alpha double dot plus eta squared alpha minus alpha naught is equal to 0, close to the equilibrium point. Let's change this by introducing a frictional term. So we'll have mu times alpha dot, and I should say that eta you get by expanding the equation of motion, and it turns out to be square root of c omega sine theta over a. We get critical damping when, that should be a minus, that's a plus, alpha double dot plus mu alpha dot plus eta squared alpha minus alpha naught is equal to 0, where the auxiliary polynomial associated with this equation has a repeated root, so you'd have mu is equal to 2 eta. So if you can arrange it so that your damping is of this form, in minus 2 eta alpha dot, then you'll get optimal convergence to the equilibrium point. Okay, so what we have been able to do is show that a gyrocompass will naturally align itself with true north if it's stationary, or at a particular angle which is known to true north if it is in motion. Thanks for watching.